This video goes over modulating the frequency and pitch of Phase Plant's analog oscillator. I will load an analog oscillator into Phase Plant's generator section. Phase Plant's analog oscillator oscillates waveforms to generate sound. The frequency or pitch of those oscillating waveforms can be set with the oscillator's controls. For demonstration, I will choose a sine wave, which when oscillated generates just one single frequency. For modulating the frequency of this sine wave, I will need a modulator. In other words, I will need some kind of signal that has the potential to change a part of the sound. I can choose from a number of modulators by clicking into Phase Plant's modulator section. I will choose Phase Plant's ADSR envelope by selecting Envelope under Shapes. ADSR, meaning Attack, Decay, Sustain, and Release. ADSR envelopes are a common type of modulator. The signals created with ADSR envelopes will change over time based on how the ADSR stages of the envelope are set. The signal from an envelope generally happens one time when a note is played. I can use this envelope signal to change how the sine wave's frequency will change over time when I play a note. To make this frequency change happen, I will need to route the signal coming from the envelope to one of the oscillator's frequency controls. This analog oscillator has a few places we can route it to for changing and modulating the frequency. Frequency, as in how many times a second a waveform oscillates. A way to visualize how the frequencies in a sound change is to use a spectrum analyzer. Spectrum analyzers analyze the frequencies that are happening in a sound. For this demonstration, I am going to load Ableton's Spectrum device onto Phase Plant's track in order to analyze the frequencies coming from Phase Plant. Spectrum is Ableton's Spectrum analyzer. With this device, we can see the frequencies that are being generated in the sound that are coming from Phase Plant. Now that I have an envelope loaded into the modulator section, I will route the signal coming from the envelope to a place in the oscillator that controls frequency. To route the signal of the envelope, select on the plus sign at the envelope's output right here. When you do this, you will see other plus signs appear in Phase Plant's window. These are all the places on the synthesizer that we can modulate with this envelope. One place on the analog oscillator that can change the frequency of the oscillator is the shift settings. The shift settings change the frequency of the oscillator by linear frequency amounts. Shift adds or subtracts a fixed value in hertz. I will select the shift settings right here. When I do this, a dotted line appears indicating that a signal has been routed from the envelope to the shift controls in the oscillator. Also, small circles will appear at the end of the dotted line. When you hover over the small circle that appears at the output of the envelope, the dotted line showing the routing will appear. It will also appear when you hover at the input of the oscillator. When I'm not hovering in the small circle, the dotted line disappears, but the routing still remains. Also, the circles remain at the input of the oscillator and output of the envelope. These circles indicate that a modulation routing has been set at the location of the circles. The oscillator's shift settings values can change the frequency of the oscillator by small linear frequency increments. Shift adds or subtracts a fixed value in hertz. Hertz is how we measure frequency. Frequency is related to the notes in music. I will play a G note. We can see what frequency this note generates in Spectrum's window. This note generates a 100 Hz tone. When I change the values of the shift settings while playing a note, I can see in Spectrum that the frequency of the sine wave changes by small amounts when I change the values here. You can change the shift values by selecting the value and dragging up or down. Rather than changing values manually, dragging up and down like this, instead, we can create this change or another change of our choice with the signal coming from the envelope. I will adjust the settings of the envelope based on how I would like the oscillator's frequency to change over time. I want the frequency to go up and down. In other words, I want the frequency of the sine wave to increase then decrease. I am only going to use the attack and decay stages of this envelope based on what I need for this sound I'm trying to create. I will adjust the attack and decay settings both to about 1 second, and I will put the sustain at 0. With sustain at 0, only the attack and decay stages of this envelope are used. To change the ADSR settings, I can drag the points of the stages in the envelope's graphic window right here, or by changing the values of the stages here below. I am going to set the envelope so its signal goes up and down for about 2 seconds. Now, when I play a note, I can see in the envelope's graphic a dot moving across the stages of the envelope's graphic, going up and then down when a note is played. When I play and hold a note, it triggers the dot to start moving through the stages. In other words, a note played tells the envelope when to start its signal. To move the dot through both the attack and decay stages while playing a note takes about 2 seconds with my current settings. For 1 second, the envelope signal is increasing in value, and for 1 second, it is decreasing in value. We can now use the signal to change the frequency of the oscillator so that it goes up and down over time for about 2 seconds. With these settings, the signal will have the potential to increase the frequency of the oscillator for 1 second, then decrease the frequency back to the frequency it started from for another second. To make this happen, I must set an amount for how much the signal will increase and then decrease. What is set with the amount is what percentage of the modulating signal will be sent to the modulator. In this case, the amount we set will determine how much the frequency will increase and then decrease. In other words, how much the frequency will go up and down. To set this amount, select into the small circle next to the output of the envelope or input of the oscillator. Then click and drag up or down. When doing this, a percentage of the small circle fills in like a pie graph. Notice below the circle a number changing that indicates the percentage being set. This can be set to either a positive value or a negative value. I will set it to about 15% positive. Now when I play a note, we can hear the pitch going up and down. With this envelope's modulation amount settings, we can see in Spectrum's window that when I play a G note at around 100 Hz, the sound will increase to about 400 Hz, and then go back down to 100 Hz, with a 300 Hz change in frequency. If I right-click into the circle, a window will open showing the values I currently have set. The value below the percentage indicates how much frequency change will happen if I have an amount of 15% set. The value indicates that the frequency will change by about 300 Hz with an amount of 15% set. This is nice if you are trying to create specific note or frequency changes in a sound. You can change the amount percentage here by selecting and typing a value. I will type and change the modulation amount to 5%. Now we can see that with a 5% setting, the frequency will change by about 100 Hz. When a note is played, we can see this indicated in Spectrum's window as well. I will now set the amount value to a negative setting by typing in a negative value. Now when I play a note with a negative amount setting, the frequency will start to decrease in its attack stage rather than increase. Then when it reaches the decay stage, it will increase rather than decrease back to the original frequency. The shift settings are not the only place this oscillator's frequencies can be changed or modulated. To remove a modulation routing, you can double-click into the circle at the input or at the output of the routing. I will remove the modulation signal from the envelope to the shift settings by double-clicking in the circle. Now I will route its signal to the semitones settings by selecting the plus sign at the output, then selecting the semitone settings. The semitone settings change the frequency and values of semitones. Semitones are the notes in music. This changes the values in terms of note pitch. Pitch is musically how we perceive frequency. With pitch, when you increase or decrease these semitone values in terms of how the frequency is changing, the frequencies do not change in a linear way. They change in an exponential way. Frequency doubles for every increasing octave. This is exponential. There are 12 semitones in an octave, so for every 12 semitones of change, the frequency will double. Or you could say, change exponentially. Simply put, this means that the frequency of the oscillator with the semitone settings will increase the frequency in greater and greater amounts compared to the linear frequency changes of the shift settings, exponentially versus linearly. When setting the amount of modulation at the semitone settings, the frequency will change based on semitones. It may be beneficial to type in a modulation amount value. The semitone settings values in this window represent the amount of semitones the pitch will be modulated. This is helpful if you want your frequency modulation changes to happen by perfect notes. For example, if when modulating frequency, I want the sound to change from note G1 to the note G2, to do this, I will type in a modulation amount value of 12 semitones. Now when using the same attack and decay envelope used previously as a modulator, while playing a G note at 100 Hz, I can hear and see in Spectrum that the pitch will go up and down by 1 octave, from 100 Hz to 200 Hz. The values set in the semitone settings are equivalent to the number of semitones the frequency will be modulated in. In other words, this is the range the frequency will change in. If I set the value to 5, the frequency will go up and down by 5 semitones. Or if I set it to 10 or 20 or whatever is set, this will be the modulation range of frequency change based on semitones. Another place in this oscillator's controls, besides the shift and semitone settings, where you can route modulation for frequency change, is the harmonics settings. In between the semitones and shift settings are the harmonic settings. The harmonic settings change the frequency by harmonics. Harmonics are multiples of a specific frequency. I will remove the routing from the semitone settings and route the same attack and decay envelope's signal to the harmonics settings. It is possible to have modulation routed to more than one place at the same time if you choose. In that case, whatever the modulation amount values that are set will be added together. But for this demonstration, I am using just one modulation routing at a time. The harmonic settings change the incoming frequency by multiples. In other words, these settings multiply the value of the incoming frequency by the set number. 1 times, 2 times, 3 times, 4 times the frequency, etc. These frequency multiples generate what are called harmonic frequencies. When you change the amount of modulation with these settings, you are increasing or decreasing the frequency change by harmonic values. If I type in and set the amount of modulation to a value of 1, we will see in the window that this value will add 1 harmonic to the frequency being generated, which means the frequency change with this amount of modulation will be 1 harmonic. Now when I play a G note at 100 Hz, I can hear and see in spectrum that the frequency will change to 200 Hz and back again. In other words, it changes by 1 octave. We know that doubling a frequency will give you an octave. 1 harmonic above the original pitch is 2 times the frequency, which doubles the 100 Hz to 200 Hz. Which is an octave above 100 Hz. That is, with this modulation amount value set, the modulation range will increase and decrease from 100 Hz to 200 Hz, then back to 100 Hz, based on the attack and decay envelope settings. I will now change the modulation value to +2, which means it will change the modulation frequency range by an added 2 harmonics. When changed to +2, we see in the harmonic settings window that this will multiply the frequency by 3. 100 Hz times 3 is 300 Hz. With this set, when I play a G note at 100 Hz, it will now increase and decrease the frequency by 2 harmonics above 100 Hz, which is from 100 Hz to 300 Hz. Between the shift, semitones, and harmonic settings, your choice for which frequency setting to choose for frequency modulation depends on the amount of frequency change you wish to have in a sound. Another type of modulator that is commonly used to modulate frequency in analog oscillators are LFOs, low-frequency oscillators. LFOs have a signal that repeats over time, compared to an envelope whose signals generally only happen once. I will delete the envelope by selecting the X in the corner of its graphic user interface. Then I will select into the modulator section and choose and select an LFO as a possible modulator. In Faceplant, the same way to route an LFO's signal is the same way an envelope signal is routed, by selecting the plus sign at the output and choosing a modulation destination. Also, the way to set a modulation amount for the LFO signal is the same way that an envelope's amount is set, and it behaves the same way for LFOs as it does for envelopes. In other words, the amount settings increase or decrease the value of the modulation signal by changing the amount value. This applies to all of the other modulators as well. Faceplant's LFO defaults to a triangle waveform. Notice that this is a similar shape to the way I set the envelope earlier. The difference with LFOs compared to envelopes, once again, is that these increase and decreasing changes will repeat rather than just happen once. I will route the LFO's output to the shift settings and set a modulation amount of 10%. Now when a note is played, the frequency will repeatedly go up and down. Larger modulation amounts create greater pitch changes, and smaller modulation amounts create smaller changes. Vibrato is a musical term that describes a small repeating frequency change in a held note. You can create a vibrato-like sound with a synthesizer by modulating frequency with an LFO. I will set the modulation amount from the LFO to 0.5%, half a percent. Then I will change the frequency of the LFO to about 6 Hertz. LFOs are just like oscillators, except they oscillate at low, inaudible frequencies. Like analog's oscillators' frequency settings, the LFOs are also measured in Hertz. With these settings, now when a note is played, we hear the sound of vibrato.